Good morning, everyone. In this lecture of computer networks, we will be discussing about audio and video compression. Now let's get started. Initially, I would like to tell you about what is data compression. Data compression is a process of reducing the volume of data by applying a compression technique, right? And the resulting data that we got is known as compressed data. Now, the goal of data compression is to represent an information whose source can be a data file, an image, or anything else as accurately as possible using the fewest number of bits. For example, if I have a number as 25.88888888, then this string can be compressed as 25.9 times 8. It can be interpreted as 25.98, and the original string is perfectly recreated, just written in a smaller form. Right. Now, moving on to the next slide, that tells about the opposite of the compression process, that is decompression. The process of reproducing the original data from the compressed data is called as decompression. And the resulted data that we got from the process of decompression is known as the decompressed data. Now, there can be a variety of reasons to compress the data. For example, we have to reduce the file size, or we have to save the disk space, or we have to increase the transfer speed that is given at a particular data rate, or we have to allow real-time transfer at a given data rate. These are the reasons to compress a file to get the desired outputs, right? Now, moving on to a general categorization of compression techniques that are of three types. First, comparison takes place between lossless and lossy compression technique. The second comparison takes place between symmetrical and asymmetrical compression technique. And the third one comprises of software and hardware compression techniques. Right. Now, initially, I would like to tell you what is lossless and what is lossy compression. That we'll be dealing in this lecture. Now, in lossless compression technique, we have a data that is to be compressed, and if the decompressed data is same as the original data, it is referred to as lossless compression. Otherwise, the compression is lossy. That means if the compressed data is equal or is same as the original data, then we confronts it as lossless compression. And if the decompressed data is not the same as the original data, then it means that it is lossy compression. Now, the second comparison takes place between symmetrical and asymmetrical. In symmetrical compression, the time required to compress and to decompress the file are roughly the same. And in asymmetrical comparison, in asymmetrical compression, the time taken by compression is usually much longer than decompression. Now, moving on to the third comparison between the software and hardware compression technique. A compression technique may be implemented either in hardware technique or in software form. Now, as compared to software codecs, coder and decoder, hardware codecs offer better quality and performance. Why is it so? Because we have a dedicated hardware for the compression process, or we have a dedicated codec. And if we have a dedicated codec, right, in the hardware form, that it must be supplying a better quality and performance. For example, in case of a graphics card, we have some dedicated graphics that is pre-installed in a system, right? That means of 256 MB or 512 MB. But if we purchase an external graphic card, that certainly offers a better pixel shader or a better graphics quality, right? That means if we apply a hardware or external hardware codec, then it will offer better quality as well as performance. Now, moving on to the next slide, let me give you a brief introduction what is lossless compression. Now, in lossless data compression, the integrity of the data is preserved. That means the original data and the data after compression and decompression are exactly the same, because in these methods the compression and decompression algorithms are the exact inverses of each other. That means no part of the data is lost in this process. Redundant data is removed in compression and added during decompression. Lossless compression methods are normally used when we cannot afford to lose any amount of data. Now, this lossless compression can be of various types. For example, run length encoding scheme or Huffman coding or LZW encoding are the types of lossless compression. And moving on to the lossy compression, now here our eyes and ears cannot distinguish the subtle changes. Now in such cases we can use a lossy data compression method. These methods are cheaper and they take less time and space when it comes to sending millions of bits per second for images and video. Now here one disadvantage is that the decompressed data or the compressed data are not the same. That means there may be minute changes. Now here several methods have been developed using lossy compression techniques. For example, JPEG, that is popularly known as Joint Photographic Experts Group. Now it is an encoding technique that is used to compress pictures as well as graphics. Now moving to a popular video format, that is MPEG, that corresponds to the moving picture experts group. Now it is an encoding technique that is used to compress the video, and MP3, that is full form is MPEG audio layer 3 for audio compression. Now let us view the detailed bifurcation of lossy and lossless compression. Here we have data compression methods that are of two types, lossless and lossy. Now in this lecture we'll be discussing about the lossy methods, that is for image, video as well as audio compression. That corresponds to three values, that are JPEG, MPEG and MP3. Now moving on to the JPEG format. Now what is JPEG? An image can be represented by a two-dimensional array, right? Two-dimensional array, certainly a table or a picture elements, that corresponds to the pixel value. A grayscale picture of 307 200 pixels is represented by 2457 600 bits, and a color picture is represented by 7372 800 bits. Now here in JPEG, a grayscale picture is divided into 8 by 8 pixel blocks to decrease the number of calculations, because as we will see shortly, the number of mathematical operation for each picture is the square of the number of units. Now see here, consider an image that is a grayscale picture and it is divided into blocks of 8 by 8 pixels, right? Now we have to focus on the entire process of JPEG compression. Now the whole idea of JPEG compression process is to change the picture into linear set of numbers that reveal the redundancies. Here the linear corresponds to the vector values. The redundancies, that is the duplicate values, that means the lack of changes can then be removed by using any one of the lossless compression methods we studied previously. A simplified version of this process is shown in figure below. For example, if I have a blocked image, DCT is the first process. DCT is basically comprises of the discrete cosine transformation, and then we have to move on to the second process, that is quantization process, and then we move on to the lossless compression, and then we get the compressed image. Now moving on to the first process, that is DCT, that is the discrete cosine transformation, we get the picture as it is. Now in this step, each block of 64 pixel goes through the transformation, right, called as discrete cosine transformation. Now here the transformation changes the 64 values so that the relative relationships between pixels are kept but the redundancies are revealed. Now few indexes are mentioned here. For example, p x comma y defines one value in the block, while t m comma n defines the values in the transformed block. Now, what is P and what is T? We will be focusing that on the next slides, right? Now, for example, to understand the nature of the transformation, let us show the result of the transformation for three cases, in which the first case deals with a uniform grayscale. Now, if I have a block 8 by 8, then in the first process, that is a px comma y, we have a uniform grayscale value, that is 2020, that is 20 value is uniformly distributed into the entire area. Now after the transformation we apply on px comma y, we get the value as of t m comma n, that is the uppermost value, uppermost value, that is 160, and the rest of the values are of 0. Now moving on to the second, this was the first case. Now moving on to the second case. In the second case, we have a block with two different uniform grayscale sections. There is a sharp change in the values of the pixel from 20 to 50. When we do the transformation, we get a DC value as well as a non-zero AC values. However, there are only few non-zero values clustered around the DC values, and most of the values are of 0. Right. Now moving on to the third slide, that is of the gradient grayscale. In the third case, we have a block that changes gradually. That is, there is no sharp change between the values of the neighboring pixels. When we do the transformation, we get a DC value with many non-zero AC values. Right. Now among all three, we get some conclusions, right? That means the transformation creates tables T from table P. The DC value is the average value when multiplied by a constant of the pixels. The AC values are of the changes, and lack of changes in the neighboring pixels creates the zeros. Now we move on to the second process, that is of quantization. Right. Now after the T table is created, the values are quantized to reduce the number of bits needed for encoding. Right. Previously in quantization, we dropped the fraction from each value and kept the integer part. Here we divide the number by a constant and drop the fraction. This reduces the required number of bits even more. In most implementations, a quantizing table of 8 by 8 defines how to quantize each value. The divisor depends on the position of the value in the table T. This is done to optimize the number of bits and the number of zeros for each particular application. Note that the only phase in the process that is not reversible is the quantizing phase. Right. Now we lose some information here that is not recoverable. As a matter of fact, the only reason that JPEG is called lossy compression is because of the quantization phase. Now moving on to the third slide of this process corresponds to the compression. Now after quantization, the values are read from the table, right, and redundant zeros are removed. However, to cluster the zeros together, the table is read diagonally in a zigzag manner rather than row by row or by column. The reason is that if the picture changes smoothly, the bottom right corner of the table T is all zeros, right? Now here JPG usually uses the run length encoding of the compression phase to compress the bit pattern resulting from the zigzag linearization. Now we can move on to the graphical illustration of this. Now here you can see the zigzag manner that is received in the table m comma n, right, and the nodes that is occurring in a zigzag manner are mentioned in the result of the table, as if the first value is 20, then 15, then the second row first element 15, then the third row first element 12, then 17, then 12, then 0 0 0 0, then 0 0 0 0 0, and so on. Right. Now we come to the video compression. Right. Now what is video? Video is composed of multiple frames and each frame is an image. Now we can compress video by first compressing images. Now there are two standards that are prevalent in the market, that are JPEG is used to compare images and MPEG is used to compare video. Right? Now here the moving picture experts group method is used to compare video. In principle, a motion picture is a rapid flow of set of frames where each frame is an image. In other words, a frame is a spatial combination of pixels and a video is a temporal combination of frames that are sent one after another. Now, compressing the video, that means spatially compressing each frame and temporally compressing a set of frames. Right? Now, moving on to the next slide that comprises of the spatial and temporal compression. Spatial compression of each frame is done with JPEG or a modification of it, and each frame is a picture that can be independently compressed. Now moving on to the temporal compression. In temporal compression, redundant frames are removed. Now when we watch television, we receive 50 frames per second. However, most of the consecutive frames are almost the same. For example, when we are talking to someone, most of the frame is the same as the previous one except the segment of the frame around the lips which changes from one frame to another. Right? Now moving on to the next slide that corresponds to the compression of data. To temporarily compress the data, the MPEG method first divides the frame into three categories. The first one is I frame, the second one is P frame, and the third one is B frame. Now here the I frame corresponds to the intra-coded frame. That is an independent frame that is not related to any other frame. That means not to the frame sent before or not to the sent frame after. They are present at regular intervals. For example, every ninth frame is an I frame. Now an iframe must appear periodically to handle some sudden changes in the frame that the previous and the following frames cannot show. Also, when a video is in broadcast mode, a viewer may tune in to any time. And if there is only one iframe at the beginning of the broadcast, the viewer who tunes in late will not be able to receive the complete picture. Right? For example, if I have to broadcast a video, right, then there may be the people who can tune in late. That means there may not be all persons who tune in at the starting of the program. That corresponds to this value of iframe. Now here the next one is pre-frame. P frame. Now P frame is here is the predicted frame that is related to the preceding iframe or P frame. In other words, each P frame contains the changes from the preceding frame. Now the changes here cannot cover a big segment. For example, for a fast moving object, the new changes may not be recorded in a P frame, and P frame can be constructed only from the previous I frame or P frame. P frame carry much less information than other frame types and carry even fewer bits after compression. Now moving on to the third type of the frame section, that is the last type, is of B frame. Now here B frame is a bidirectional frame and is related to the preceding and following I frame or P frame. In other words, each B frame is relative to the past and the future. That means one point that is to be noted here is of that B frame is never related to another B frame. Now there are certain conditions of I frame and B frame. That means the one particular frame cannot come after it. So all these conditions are mentioned in the next slide of that is depicted by a figure. For example, if I have 7 frames, then the frames are mentioned in A figure and its construction are mentioned in the diagram number B that is present on the right hand side. That means the first is I, then B, then B, then P, then B, then B, then I. Right? Now that's it for the MPEG frames. Now moving on to the second aspect of today's lecture, that is audio compression. Audio compression can be used for speech or music, right? That means for speech we need to compress a 64 kilohertz digitized signal, and for music we need to compress a 1.411 megahertz signal. Now, two categories of techniques are used for audio compression. The first one is predictive encoding, and the second one is perpetual encoding, that we'll be discussing in next slides. Now, the predictive encoding deals with the differences between the samples that are encoded instead of encoding all the sampled values. That means this type of compression is normally used for speech. Now, here are several standards that has been already defined, such as GSM, that deals with the 13 kbps, and then G.729 that deals with the 8 kbps, and G.723.3 that deals with 6.4 or 5.3 kbps. Right, now dealing with the another type of perpetual encoding that deals with the MP3. Now, the most common compression technique that is used to create CD quality audio is based on the perpetual encoding technique. Right, now this type of audio needs at least 1.411 mbps. This cannot be sent over the internet without compression. Right, now mp3 that deals with the mpeg audio layer 3, a part of the mpeg standard, uses this type of technique. Now, perpetual encoding is based on the sciences of psychoacoustics, which is the study of how people perceive sound. The idea is basically based on the flaws in our auditory system. Now, some sound can mask other sounds. Masking can happen in terms of frequency or time. Now, in frequency masking, a loud sound in a frequency range can partially or totally mask a softer sound in other frequency range. For example, we cannot hear what our dance partner says in a room where a loud heavy metal band is performing, right? And in temporal masking, a loud sound can numb our ears for a short time even after the sound has stopped. Now, MP3 uses these two phenomena, frequency and temporal masking, to compress the audio signals. Right, now this technique analyzes and divides the spectrum into several groups. Now, here 0 bits are allocated to the frequency ranges that are totally masked, and a smaller number of bits are allocated to the frequency ranges that are partially masked, and a larger number of bits are allocated to the frequency ranges that are not masked. Now, here MP3 produces three data rates that are 96 kbps, 128 kbps, and 160 kbps. The rate is based on the range of frequencies in the original analog audio. Right, now that's all for the audio and video compression. Hope you like it. Thank you.